All right, everybody, let's continue chapter 24 as we look at Gauss's law. Let me write Gauss's law again. So here's Gauss's law. We have flux equals charge in over epsilon zero. Now, we talked about flux earlier, right? So let me actually go back and say this is all with the, assumption that we have a Gaussian surface, right? We pick a Gaussian surface and we calculate the flux through that Gaussian surface. That's this right here, right? When we count flux. And remember, to calculate flux, if you match the symmetry, those conditions that I mentioned in the last video are there. Then it's just EA, okay, where A is the surface area of your Gaussian surface, or at least the surface area where the flux or the electric field is going through. And on the right side is Q in. Okay, so this is charge inside your Gaussian surface. Inside, oops. Gaussian surface here. Okay, so it really comes down to two calculations. You have flux inside, or sorry, not flux, charge inside, I should say, charge inside and flux, right? And in practice, when we use Gauss's law, we're gonna have to do both calculations in a single problem. So we talked about how to get flux, and in future problems, you'll see that we don't know E. E will remain an unknown. We'll know surface area. Okay, we'll have equations for that depending on what symmetry, what shape we're dealing with. Okay, so E will remain here, but we would have to know how to find Qn, and that's what I want to spend my time on in this video, calculating Q inside. So we'll do a few examples, but in future videos, the next video is coming up. We'll still do it because it'll be part of calculating Gauss's law. So you'll see more examples of calculating Q inside. So I just want to give you a couple examples, just focusing on getting that charge inside a Gaussian surface. All right. So our first example is just a sphere with a total charge Q, and I should add here that it's going to with uniform charge density with uniformly charged. Okay, so let me put a sphere here. Let me do it like this, actually. Okay, so there's my sphere. I'm gonna have a radius, capital R. Okay. So what I want to do is find the Gaussian, or find the charge inside a Gaussian surface when. Here, I'm going to do it this way. When lowercase r is less than greater. Okay, so we're going to do it when lowercase r is greater than uppercase r, so or less than uppercase r. So what I mean by that, we're looking for our Gaussian surface, which a Gaussian surface in this example would just be another sphere. So I'm going to pick another circle. Or another sphere here. Try to have that coaxial there. Okay. So we have the Gaussian surface, and I picked a sphere because the sphere matches the symmetry of the problem, right? We have a sphere of charge, so I'm going to pick a sphere from my Gaussian surface. And that Gaussian surface will have a radius of lowercase r. Lowercase r. Okay, so I want to find the charge inside when r is less than capital R, when my Gaussian surface is smaller than the actual sphere, than the actual charge itself. Okay, so how do I find Q inside? I could find Q inside by using charge density. Let me go. Okay, remember what charge density is? Well, in this case, we're talking about a volume, right? A sphere of charge. And I'm going to say that this is my surface charge density is, or no, volume charge density is charge over volume. Okay, so in our case, we have a total charge Q, and the volume that this charge is dispersed in is that sphere with capital R, is that gray sphere. So it's 4/3 pi r cubed, right? The volume for my sphere. So that's my charge density. So I want to use charge density to calculate the charge inside. Okay, now this charge density stays constant, right? So it's a uniformly charged. So the charge density is constant throughout, which means that ratio of charge over volume holds no matter what section of that sphere I'm looking in. So if I'm looking at the charge inside the Gaussian surface, then I just need to divide that by the volume of my Gaussian surface. I'll put Vg. Okay, so let me just rearrange this. To find Q inside my Gaussian surface, it's just charge density times Vg. All right, simple as that. So I'm gonna plug in for both quantities. I'm gonna plug in for charge density. This is my charge density down here. And I'm gonna plug in for Vg. So let me plug in for charge density. So charge density is that what you see on the right side. So Q on the left side, I should say, Q over 4 over 3 pi r cubed. All right, that's my charge density. And then what do I plug in for my volume here? Volume of G, Vg. This is a Gaussian volume. So the volume of my green sphere. Okay, well, it's still a sphere. So so I'm still going to use the same equation. So 4/3 pi. And instead of capital R, since I'm talking about the Gaussian surface, I'm going to do lowercase r. And all we need to do now is simplify. Right, so to simplify this, let's see. So 4/3 cancels out. The pi's cancel out. And I get my charge inside. Charge inside my Gaussian surface, charge inside my green circle here, my green sphere, is just going to be the total charge in the gray sphere, in the sphere charge itself. So that total charge times this ratio, r over lowercase r cubed. Okay, now the reason why that works, what I did here, is because of this keyword, uniformly charged. So that means that this ratio here, rho equals Q over V, where this is total charge and I guess you could think total volume, volume of the ball charge itself. Okay, so this ratio holds no matter what section of the charge you're looking at. So if I looked at just a charge inside my green circle, which is what I did here, this ratio still holds. All right, it still equals my same charge density because it's uniformly charged. All right, so after that, it was just a matter of just doing some algebra here, right, to get my final answer. Now let me change the situation. Let's say, so I guess I never put the question. So let's find the charge inside Gaussian surface when, and this time, I'm going to say capital R is less than R. So I'm going to make my sphere different size. Let's see. All right, get a little bit bigger. Okay. So now there's my sphere. That means my radius is now something like this. Okay. So now my Gaussian surface is larger. Now the reason why I would want to do that is because that would give me I would eventually use this to find the electric field outside the sphere. So I would just kind of moving ahead of what we're going to be doing in the next video. The electric field would be right here, right, going through this, and so using Gauss's law, I could find the electric field, you know, at this distance, distance from the center. Okay, but right now we're just trying to calculate charge inside. So how do we calculate charge inside my Gaussian surface now? Okay, how much charge is inside this green circle? Well, in this case, it's pretty easy. I have no charge here, right? All this space, or this white space you see, is just empty, no charge. All the charge exists right here on the chart, on this ball. So how much charge do I have on this ball? Well, the problem told me, Q. So it's as simple as that. Q inside, oops. Q inside my green circle is just equal to Q. Right, and that doesn't matter how big that circle gets. If I made my green circle, extremely big like this, well, it's still the same amount of charge in there because again, all this space here is empty space. All the charge exists within this gray circle. Right. So I think let me see if I can make this. All right. Well, I don't know if I could get back to the same size I had it. All right, something like that. Okay, so in that case, it's just charge inside. All right, so pretty, I think, straightforward example. Whenever you have uniform charge density, it does get it gets pretty easy. All we have to do is use that ratio, right? Charge over volume. But of course, that's for a volume charge density. We could do the same application if we're talking about surface charge density or a linear charge density, which we will do examples of later. But it's the same general idea here. All right, so let me change the situation a little bit here. What if I had a sphere with a non-constant charge density? So now let me draw the sphere again. Let's see here. Okay, so let's say I had a charge density that is such that the charge increases as you get further from the center, right? So the charge density increases. So more you have, and this is true in all directions here. So the more you go from the center, the more charge is located per volume, right? Per unit volume. Okay, so this is just an example of something like that, something for us to use to show you how to do this calculation. And let me give a function here for our example. So let's say rho, charge density, equals some constant, which I'll call alpha. Okay, some number, and we'll say it's r squared. Okay, so my charge density is then a function of r. So maybe I could write it like this actually. So charge density is a function of r. Okay, and that density will hold from 0 to capital R. Okay, so capital R being my radius again. Capital R. Okay, so how can I find charge? How can I find the charge inside a Gaussian surface? So well, first we got to make up a Gaussian surface. Let's say a Gaussian surface is kind of like how I started last time, like that. Okay, so I'll say that this is lowercase r. Okay, so same idea, find charge inside the Gaussian surface when r is less than r. Lowercase r is less than uppercase r. So when we're still within that sphere. Okay, so last time in the previous example, I said, well, let's just look at charge density. That charge density equals Q over V. I'm going to put a different color here. Okay, now that worked last time because that, like I said, that ratio stays constant throughout the charge. In this case, it doesn't, right? Charge density is given to us by a function here. Okay, so it doesn't stay constant. Well, I could write this though, if I picked a small little piece of volume here, and I'll call it dV, then the charge density at that little dV would just be dq over dV. Let me write that a little bit neater. So dq over dV. Okay, that's my charge density at this very, very, very small volume, this infinitesimally small volume. Okay, so the reason why I write it this way is because now I could rearrange it and solve for dq. So I go dq equals rho dv. Okay, and then if I integrate both sides, the integral dq just becomes q, and on the right side, I'm just going to write it as integral rho dv. Okay, so to find the charge inside, I'm going to have to use this integral because rho, like I said, is not constant. Rho is a function. So I can't just use that ratio that I used last time. Okay, so how do I actually solve this? Well, first of all, let's deal with dv. What is that? How do I do? I mean, I know what it is. It's a small section of volume here, but actually, how do I actually solve for this? Well, you could, for that you would have to do to go to the basics or to the most, I guess, fundamental approach. You would need to do a triple integral to find volume or to find dv. But triple integrals aren't required for my class, so I'm going to show you a kind of a trick here. Assuming this density only depends on radius, on distance from the center, which it does, that's what the function gives me. Let's look at volume here. Volume for a sphere is 4/3 pi r cubed, right? So that's the equation for any sphere, for the volume of any sphere. Actually, I'm going to run out of space here, so let me move this. I'm going to move this over. Yeah, I might have to erase this. Okay, so 4/3 pi r cubed. Now I'm going to take a derivative here. I'm going to take the derivative with respect to r. Okay, so I'll put t dr on both sides. Okay, so on the left side I get dv over dr, and on the right side I get 4 pi r squared. All right. Now 4 pi r squared, that is the area, surface area of a sphere, and that's going to become important in a second. I'm going to show you why. So let's solve for dv. dv equals 4 pi r squared dr. Okay, so that's what we're going to use for this dv, because we're dealing with a sphere. That's not always going to be dv, because you won't always deal with a sphere. It'll be a different shape depending on what problem you're doing. But for our problem, because we're dealing with a sphere, this is what we're going to use for dv. Now, what this physically means, like I said earlier, 4 pi r squared is the surface area of a sphere. So you can imagine that we have a sphere here with a small little distance of thickness. Okay, so I'm kind of exaggerating this, but oops. Okay, what this dv is the volume between this shell here. Okay, where the inner radius and the outer radius aren't very different, because the dr is such a small thickness, right? This is what this dr is. Dr is the thickness of the shell, and the radius, this radius here, compared to this radius out here, they're the same radius, because that dr is so infinitesimally small that there's not a noticeable difference between the inner radius and the outer radius, right? We're taking the limit to when dr goes to 0, that those two radius become. So we're getting a small little piece of volume, but it's not this little piece here. It's not the same idea. The volume that we're looking at here is this volume of a shell. Okay, so what we're doing when we're integrating is that we're adding all these shells together to get the total volume, right? Depending on where our limits are at. Okay, so that's where that's the significance of that. So like I said, I'm gonna have to erase some of this. I'm running out of space here. Okay, So I'm going to do Q, oopsie. So Q equals integral rho, which again, remember is a function of r, and dv is 4 pi r squared dr. Okay, so we're integrating with respect to r. Now, remember what we're trying to do here. We're trying to find the charge inside my Gaussian surface when r is less than r. So here's my Gaussian surface. I am only interested in finding the charge, adding up all those shells together from a radius of 0 to the radius of this green circle of my Gaussian surface. Okay, so my integral, my limits here are 0 to lowercase r. All right, so let me plug in the equation for my density now. So I have 0 r, and then I have a constant alpha r squared, and then 4 pi r squared dr. And of course, I could simplify that. Let me take out all my constants out. Alpha 4 pi 0 to r, and I'm left with r to the 4 dr. Okay, and then which I took the integral for that. R to the 4 gives me r5 over 5, r to the 5th over 5, and I get my answer. Alpha 4 pi, my constants, over 5 times r to the 5th. And that is my charge inside my Gaussian surface. Okay. Okay, now let's see if I can fit in what I have here. So so that's the charge when the Gaussian surface is less than capital R. What about when capital R is less than lowercase r? So again, this is I'm going to change my radius here for my Gaussian surface. I could pick it. Oh, there it goes. You can make it a little bit bigger. Okay, and which means my r, but not vector, but my radius here, it's going to look something like that. Okay, so when r is less than r, so I want to find qn again. Q inside my Gaussian surface, but now my Gaussian surface is much larger. And also, here's a quick side note: when I say qn, I don't mean inside my charge. It's this qn is always referring to inside your Gaussian surface. Okay, inside that imaginary surface, which we call the Gaussian surface. Okay, so I want to find out how much charge is inside here. Okay, now it would be a mistake just to keep the same integral, or at least the same limits, because look at what the limits is saying. You're taking the density times 4 pi r squared dr from 0 to r. Well, from 0, okay, that makes sense, but all the way to r, well, there's nothing over here. Right, this white spot between the actual charge and your Gaussian surface, it's all empty charge. So your density is 0 here. Your integral should be 0 for this empty spot. So we don't want to integrate from 0 to r. That I mean, you could split it up into 0 to capital R and capital R. Let me show you what I mean. 0 to capital R, because that has a density, right? Times 4 pi r squared dr. Plus integral from r to lowercase r, which would be this space here, this space right there, and density times 4 pi r squared dr. Okay, now what is your density here? When you go outside and in that white spot, right, between the charge and your Gaussian surface, what's your density right there? Well, your density here is 0, right, because there's no charge here. So if that's 0, then that means this whole integral here is 0. Okay, so when we are looking on the outside here, when my Gaussian surface is on the outside of my charge, I'm only interested to go in capital R, right? I stop here, because that's where the charge stops. That's where the charge stops existing. There's no charge existing outside of that radius. So I just go to that capital R. but it's the same integral. So you're gonna, everything else is the same. All the algebra and calculus is the same. All we're doing is different limits here. Okay, so we would get, let me erase this 0. So our answer would be alpha 4 pi over 5, and then capital R to the 5th. All right, let me jump ahead here since you guys know flux, right? What we're working towards is using Gauss's law. Flux equals Qn over epsilon 0. So if we're looking at the case when R is greater, lowercase uppercase r is greater or less than, I should say, lowercase, I can't seem to get this right. Uppercase r is less than lowercase r, which is a picture shown here. And I say find the flux going through what? Well, you're trying to find flux, you always look to the Gauss's law, or the Gaussian surface. You look to the flux going through the Gaussian surface. You do not look to the flux, or you do not look at the flux going through this surface. That doesn't make sense. We're not interested in the flux going through the charge. We're always interested in the flux going through the Gaussian surface here. Okay, so even in this flux, you don't ever use capital R. In this equation for flux, you use lowercase r. Like for example, you're going to calculate EA. Well, what do you plug in for area? For area, you're going to plug in the surface area of a sphere, which is 4 pi lowercase r, because we're talking about the Gaussian, squared. Okay, that's what you plug in for A. Okay, so even though for Q inside, you're going to capital R because you're trying to find a charge inside, for flux, right, you're always looking at the Gaussian surface there. Okay, so I just want to mention that because that's always a point of confusion or where a lot of students make mistakes, is that when you're trying to find flux, you might use the capital R, right, the physical radius. Well, that's not true for flux. Flux, we always use a Gaussian surface, right, our imaginary surface for our calculation. Okay, so that was more of a tangent. Well, of course, we're going to do examples with that in the future. All right, one more example for our lecture here. I want to do a cylinder of charge. So how do you calculate the charge inside a cylinder? So I'm going to have a sphere here, or let me draw a cylinder of charge. Okay, and then I guess I'll just, I'll just keep it like that. All right, so we have all this charge in here. And for this example, let's find the Gaussian surface, find the charge inside your Gaussian surface. Okay, so it's pretty similar to the example we did earlier. We will assume that we have uniform charge density for this. So uniform charge density. Okay. And this time I'm just going to give you, instead of saying Q, I'm just going to give you the rho. Okay, so charge density is already given to us, right? Okay. If this is a problem with numbers, rho would represent some numerical, density. It would be a number itself. Okay, so we're given charge density, and I want to find the charge inside a Gaussian surface. So let's, I forgot to say, when inside, essentially, when R is less than capital R. So kind of like in the previous example, we have a physical radius. That's the radius of the charge itself, and then we're going to have a Gaussian radius. So I need to draw a Gaussian surface. What would be an acceptable Gaussian surface, right? What would match the symmetry of our problem? Well, if we're dealing with a cylinder, well, let's pick a cylinder. Right, let me do it in green again. So here's the cylinder. And I am trying to make it coaxial here with a physical cylinder. And then So this, I try to make it coaxial. Maybe it's not. Maybe it doesn't look that way. Oh yeah. Being a little bit picky here. Sorry guys. Bear with me. There. Okay, so and so that radius here of my Gaussian surface would be lowercase r. Make that. Okay, so I'll call that lowercase r here. And one more thing with a cylinder though, because in order to calculate volume of a cylinder, you don't need just radius, you need length. Right? So I'm just gonna call this L. Now, just a heads up, when we start to use Gauss's law to find electric field, right, when we're using Gauss's law to find electric field, where we use it for the complete purposes that we're headed. Length, this L that I just wrote, it's going to cancel out. Okay, so I'm just going to give you a heads up. You don't actually need a number for L. L would typically cancel out in your calculations. So so we'll see that when we do our examples in the next video. All right, so how do we find the charge inside this Gaussian surface? Well, it's pretty similar to what we did in our first example here. We could find, charge density. Charge density is defined as Q over V, right? And we said earlier that if it's uniform charge density, we're safe using this ratio. This ratio will hold no matter where in this charge you're looking at, because it's the same ratio throughout, right? It's uniform charge density. So that ratio holds. So I'm going to rearrange this, or actually, let me say, I'm going to look at the charge inside when I'm looking at my volume for my Gaussian surface, in this case, a cylinder. Okay, so I'm particularly looking how much charge is inside my Gaussian volume, and I take charge inside divided by Gaussian volume, and that gives me charge density. So I'm going to rearrange this to solve for Q inside, rho Vg. Okay, and rho is a constant this time, right? We're given rho, so the only thing we need to do is plug in for Vg. So what's the volume of a cylinder? The volume of a cylinder is pi r squared, and we're talking about Gaussians. We're looking at our Gaussian cylinder, right? So we're going to do lowercase r times L, and that's it. That's my charge inside. Okay, and just for reinforcement here, because I think you guys know how you would do this next one. So find the charge inside your Gaussian surface when uppercase R is less than lowercase r. Okay, so a different situation there. Now I'm looking at when my cylinder here is larger, which means I'll move this over like this. Let's see if I could do this. That just looks horrible. All right. Let's see. Okay, so it's kind of, it doesn't look great. So my cylinder, my Gaussian cylinder, is now larger than the physical cylinder, right, than the capital R. So in order to find the total charge inside my Gaussian cylinder, I'll do the same thing. Q inside equals rho. Now, careful what volume we're going to plug in here. The volume we're interested in, to find charge inside, we're interested in where the volume actually exists, right? So inside my cylinder, my Gaussian cylinder, there is this area or this volume here that does not have any charge existing there, right? It's all empty space. Same thing up here. There is a charge area there that charge does not exist. And even on the sides here, right? If I looked at a different, if I looked at this from a different perspective, let's say I was looking at that wire head on, you have the cylinder, that's a wire itself, the physical wire, and my Gaussian cylinder, my Gaussian surface will look something like this. Okay. So this would be my capital R, or my lowercase r, I should say. Lowercase r, and then we have our capital R here. Okay, so this is the same idea. This picture here and this picture here, same situations, just looking at it from a different perspective. This one we're looking at from the side, and you can see there's these regions that have zero charge. This one's looking at it from this one's looking at a cross-sectional area of it, and you can see all around the cylinder there's this empty space, right? No charge there. So when I'm trying to find charge inside my green circle or my green cylinder, my Gaussian surface, I don't want to include this empty space. Okay, I don't want to include that empty space. So the only volume that this charge density actually exists is a volume of the charge itself. So pi capital R squared L. Okay, we stop using our charge density once we go at this point, right? Once we reach the boundary of the physical charge, because after that, charge density drops to zero. All this whole region here has a charge density equal to zero, so they wouldn't give you charge. Only the charge within here, within the capital R. That's where the charge exists. Okay, so even though our radius is larger than the physical radius, right? Our Gaussian radius is larger than the physical radius, we don't include that lowercase r for the reasons I said. All right, so we're going to do much more examples here with finding charge inside, because this will be part of our calculations. Going back to my first slide here, we're going to be using this together now. In the next slide, we're going to use flux and charge, and we're going to have to do both calculations in one problem. And typically, this is going to be to solve for electric field. Okay, so we'll be doing that in the next video.